Welcome back everyone. We can solve one of the university question that was asked for the last university exam and is relating with memory interfacing. The question is design an interface between 8086 CPU and two chips of 16K by 8 EPROM and two chips of 32K by 8 RAM. Select the starting address of EPROM suitably. The RAM address must start at 00000H. So, how can we proceed for such a question? We need to analyze each and every part separately, right? So, we can start with the RAM part. And here, we are given with 2 units of RAM. Each unit with size 32K by 8. What is the meaning? Total 32K different word. A particular RAM chip can hold 32K word, and each word contain here 8 bits. 8 bits means 1 byte. Okay, so from this it is clear that one of the RAM chip can hold 32K different bytes, because 32K means 32K different bytes and each byte hold 8 different bits. That is the meaning of this 32K by 8 representation. How many such chips are given? 2 such chips. So total RAM space is 2 into 32K, that is 64K bytes are present in our RAM space as a total. Right. So the next point relating to this RAM space is the starting address must be at 00000H. Okay, so these are the data relating to this RAM space. So total address, we are given with 2 chips of 32K by 8 RAM. So total RAM space is 2 into 32K bytes, that is 64K bytes. We need to assign address for each and every bytes of this 64K bytes. Okay, so we need to assign different address, and the address must start from this. So the first byte address is 00000. We need to identify the range of address. The address starting from 00000. Okay, so we need to find the last byte address of this total 64K bytes. Okay, so consider this again. 64K byte means 64 into 1024. K means 1024. Okay, 64 into 1024 means this in decimal 65536 bytes total. So this is the decimal representation. Okay, but the address is starting from 00000 and we are given with total these much bytes in our RAM space, and the address starting from 0. So the address range is 0 to 65535. Total 65536 bytes. Okay, now we want to find the last byte address in hexadecimal form. What we want to do? Take the hexadecimal form of this particular decimal number. Okay, so you can use your scientific calculator for getting the hexadecimal equivalent of this particular decimal number. That is 0FFF. Okay, this is the hexadecimal representation corresponding to this. Okay, so the 0FFFF is the hexadecimal representation corresponding to this. Actually, FFFF is 65535. This is equivalent. Then why you are considering this 0 here? Because in 8086, it can address a maximum of 1 MB memory. 1 MB means 2 raised to 20 bytes. Right? So, for addressing each and every byte of our 1 MB memory, it requires how many bits? 20 bits. So, we need to represent the address in terms of 20 bits in binary. So, this is actually 20-bit binary representations hexadecimal equivalent. How it possible? this 50 actually indicate, this first 0 is actually indicating 4 zeros. Next 0 means again 4 0. Next 0 here again 4 0. Next 0 again 4 0. Next 0 again 4 0. Total 20-bit address information. Starting from right hand and proceed towards left and group each 4 bits together and find or write its hexadecimal equivalent. So that is this particular representation here. So similarly this one, the 20-bit binary representation of this hexadecimal address is, this 0 is represented using 4 zeros and this F means 4 ones, this F means 4 ones, this F means 4 ones and this F means again 4 ones. So total 20-bit address. The significance of this 20 bits here, that is 8086 can address total 1 MB memory. 1 MB means 2 raised to 20. For addressing each and every bytes of this 2 raised to 20 bytes memory, we need 20 bits. Okay, so for this 20 bits, we can group 4 bits and represent its hexadecimal address representation like this. Okay, now we can consider the next part, that is the EPROM part. Here also we have 2 chips of EPROM, each of size 16K by 8. Okay, so total EPROM size is 2 into 16K bytes. 2 into 16K bytes means here it is given that each word contains 8 bits. That is why 2 into 16K bytes. That is 32K bytes. Right. So here one more point we need to consider in case of ROM memory, whatever it may be, like PROM, EPROM, EEPROM, whatever it, you need to consider one important point, that is the address value FFFF0 must be in the range of ROM always, because while resetting the processor always pointing to this particular ROM address, because while restarting the processor start the execution from this particular address, this must be present in ROM space. Okay, so while arranging bytes or arranging address space for ROM type memory, we need to consider this point. This particular address must always comes under this ROM address space. Okay, so we can start here from the last part of our 1 MB memory and we can arrange different address space in backward. That is, the address, we can start from the last byte address, full of 1. 5, F means full of 21s, the last byte address of our 1 MB memory. Then we can allot different address space in backward direction in case of ROM, in order to include this particular address in our ROM space. Okay, so here it is clear that this particular address is our ROM space last address, last byte address. Okay, so here we want to find out the starting address of our ROM space. So here we fixed the last byte address of our EPROM. We need to derive the starting address of our EPROM. How it possible? Total, how many bytes? 32K bytes. Means 32 into 1K is 1024 bytes. That is these much bytes present in our EPROM memory. 32768 bytes, right? So it can be, and again, next point, this particular hexadecimal representation indicate the last byte address of our EPROM memory and its decimal equivalent is this. For this conversion, you can use your calculator. Base conversion, for the base conversion, you can use your calculator in Excel. Okay, so this is the decimal equivalent of this number. And these much bytes we need to allot in our ROM space. That means we need to address these much bytes in our ROM space, and the last byte address is this. Its decimal equivalent is this. So we need to find the starting address of our ROM space. How it possible? Subtract this value from our last byte address, then we get this. This much byte address we need here. Okay, so we can now allocate the address range, that is the last address is like this FFFFF, and the starting address must be 1015808 here, because we need total these much address information. These much address are possible in this range. Okay, now we can consider its hexadecimal representation. That is, we can convert this decimal value into its hexadecimal. That is, this hexadecimal representation is F8000. Okay, this can be represented in binary like this. F using 41, 8 using 1, 0, 0, 0 and 0 like this. And 5 full F can be represented like this in binary. That is total 20 bits of ones. Okay, so this is the address range of EPROM. Now consider this, the mapping, address mapping. So from our previous derivation, the RAM is total 64 KB. So the address is ranging from 00000 to 0FFFF. And for the ROM, EPROM, it is 32 KB and the address is like this. And its binary representation is marked here. Total 20-bit address representation, and the addresses ranging from 0123 up to A19, A0, A1 up to A19. Total 20 address bits. And the values are given here. Okay, so here we are given with 2 chip of EPROM. And each chip contains 16K bytes, right? 16K means total 2 raised to 14 bytes. For addressing each and every bytes of each of this chip uniquely, how many bits are required? Total 14 bits are required for addressing each and every byte of a particular ROM chip. Okay, 14 bits are required for addressing each and every bytes of a ROM chip, because one chip capacity is 16K by 8. This much address information is required for addressing each and every bytes of one chip. 16K means 2 raised to 14. So 14 bits are required for addressing each and every bytes uniquely. Okay, for this RAM space, one chip size is 32K by 8. So for addressing each and every bytes of this 32K, how many bits are required? 32K means 2 raised to 5 into 2 raised to 10, that is 2 raised to 15. 15 different bits are needed for addressing each and every bytes of a single chip of RAM here. Okay, so based on this information, we can design the configuration, memory interfacing circuit of our given situation. Okay, so here 2 chips of ROM is given, 2 chips of RAM is used. Okay, and this is 16K by 8 in capacity, this is 16K by 8 in capacity. And here this one is act as even bank and this one is act as odd bank. Okay, so one important another property of our 8086 is its address bus capacity is 16 bits. Means it can access 16 bit of information from memory at a time. It can write 16 bit of information or it can read from memory at a time. How many bits? 16 bit. Okay, so this 16 bits of information is considered as one word and it can be divided into lower byte and higher byte. Among this lower and higher bytes of 16 bit, the lower address bytes are always present in this even bank and higher byte address is always present in this odd bank. In a 16-bit information, lower byte present in this even bank, higher byte present in this odd bank. This is valid for this RAM and ROM. Both in cases, this particular information is valid. An 8086 processor can access 16-bit of information from memory. This 16-bit of information can be considered as 2 bytes, one lower byte and one higher byte. Lower bytes are always placed here in this even bank and higher bytes always present in this odd bank. This is one important point. Here also in case of RAM, one is even and other is odd bank. Odd bank contains higher byte of a word and even bank contains lower byte of a 16-bit word. Okay, that is why D0 to D7 is marked here pointing to this and A to D15 is pointing to this odd bank here and here also. Total D0 to D15, 16-bit can access by 8086 processor. And next important point, in a ROM space, ROM is read-only memory. The processor can read data from the memory. We can't write anything to this ROM space. That is why we need this memory read control signal to this ROM space. But here in this case of RAM memory, we can read data from the memory and we can write data to the memory because it is RAM. Okay, this is not read-only memory. We can read and write from, we can read from and we can write to RAM type memory. So here we need two types of control signals for controlling read activity and write activity. But in case of ROM memory, we can only perform read from memory because this is read-only memory. So here we use only one control signal for controlling read activity. Okay, next here we have these are chip selection pin CS1, CS2, CS3 and CS4. And how can we set this chip selection pin here? Here, consider this diagram again. In this ROM space, up to this 14, address bit 14, this is not 7 actually, this is 1, okay? So up to this 14, all the bits are different. Beyond this 14, that is from 15 to 19, the bits are same for ROM space. And here in RAM space, up to this 15, the address bits are different. And beyond this 15, from 16 to 19, the bits are same. So, in case of EPROM, we can use this similar address information, that is bit 16, 17, 18, 19 information for setting the chip selection. 15 to 19 for ROM and 16 to 19 for RAM and generate a particular value which is marked here as C. This is the output of a NAND gate. This can be used for setting our chip selection in case of ROM here, and this particular output, that is address information 16 to 19, is used as address information 16 to 19 is applied to this particular gate and its output is taken as one of the input for setting this chip selection. And here CS1 is set using this particular output value with BHE bar. What is this BHE? Bus high enable. This is an active low signal, that is by this over bar here. Bus high enable is used for activating higher byte of 16 bits. We have already mentioned that higher byte of 16 bit is present in this odd bank and lower byte is present in this even bank. So in order to access or in order to write this particular ROM chip, that is this old ROM bank. We need to activate this BHE bar and this C output from this gate. And this particular gate output select or set this chip selection of our old ROM bank. And here, for this particular case, the chip selection is designed like this. This event bank is activated based on the value of our least address bit, A0. So for setting the selection pin here, we use A0 at this particular gate output C. So this particular input, after passing through this gate, this particular output select or decide whenever this event bank of our ROM want to activate. Similarly, this particular output CS1 bar, that is, while applying this C and BHE bar to the gate, the value generated by this particular gate decide whenever this old ROM bank want to activate. And similarly for this RAM space. For the RAM space, this C dash is generated using A16 to A19. And for activating this old bank always contains the higher byte of 16-bit data. So for activating this old bank, we can use these inputs, BHE bar and this C dash. The output of this gate decide whenever this old bank of our RAM want to activate. And similarly for this particular even RAM bank, the least address bit A0 and this C dash decide whenever this even RAM bank want to activate. Okay, in case of 16-bit address information, lower byte of our 16-bit is activated based on the value of A0 and higher byte of our 16-bit activate based on this BHE var value. BHE means bus high enable. This is an active low signal, that is why this overbar here, and this decide whenever we want to access the higher byte of a memory word. Okay, so this is the design of our given scenario. Okay, thank you.